Okay, so we have already done the first worksheet of MCQs, and I would like you to attempt that one if you haven't already. But I'm assuming that after this worksheet two, you will obviously have an easier time solving the MCQs. I personally think MCQs are the hardest of the five papers that we have in A levels. Okay, a series of reaction based on propan-1-ol is shown. It's a primary alcohol, as you can see, because OH is attached to one carbon, which is then attached to just one more carbon. And in reaction one, you can clearly see that OH and H have gone away, and there's a double bond there. That's elimination reaction, and that happens when you have concentrated sulfuric acid. And those are the things that you need to know about: high temperature, concentrated sulfuric acid. That's what makes this. But saying high temperature is not enough. We need to be specific. So 250, 200 degrees Celsius, that's good enough. Then when you add steam in with catalyst in it, it's going to form obviously multiple products depending on where the carbocation is formed. That's the whole mechanism thing. We can use Markovnikov's rule to figure out which carbocation is more stable. And we will get two different alcohols, propan-1-ol or propan-2-ol. Then that U thing is then reacting with HBr, making V. And of course, it depends on what's happening there. So HBr, if it is concentrated, it will obviously, since it is concentrated, it will, if it is concentrated, it can provide the bromide, and that bromide can then go and replace the OH that's in there. So that is nucleophilic substitution. And based on that, you can easily see that V will be formed. And with V, something is happening. Again, V is a halogen alkane. We already know that because HBr is added there. And V then does something to form the propene again. And that basically means that V has lost the H and the Br that it was added with. So yeah, this is again elimination or condensation, giving HBr as a byproduct. On the other side, reaction 2, it is basically oxidation because you converted a primary alcohol to carboxylic acid. Okay, just give me a minute. All right, suggest a suitable reagent and condition for reaction 1. Reaction 1, as I've already explained, this is elimination reaction. So we need concentrated sulfuric acid. So concentrated sulfuric acid and high temperature, 200 degrees Celsius should be fine. Writing equation for reaction 2. So reaction 2 is oxidation. So we take CH3, CH2, CH2OH, and then we give it an oxidizing agent, which then converts it to CH3, CH2, CO2H, and there's going to be water as a byproduct. You're basically added 2 oxygen, so I'll just put 2 in there. Suggest a suitable reagent and condition. So we need a strong oxidizing agent. KMNO4 is good, K2Cr2O7 is good. So both of them must be acidified. So acidified KMNO4 or K2Cr2O7. But an important thing to remember is that when you're doing this, you need to mention the conditions as well. And conditions are heat under reflux. Why reflux? Because we do not want it to be incompletely oxidized and make aldehyde. We want it to convert completely to carboxylic acid. Give the structural formula of U and V. Okay, so U will be either propan-1-ol or propan-2-ol. Okay, and if assuming this is propan-2-ol, then we can, in fact, we can just write both of them. So one is the propan-1-ol, which is CH3, CH2, CH2OH, the one that's we started with, and the second option is CH3, CHOH, CH3. Basically, the difference is where the H and OH from water go. So they can either go to this carbon or to this carbon. Now, where they will go depends on where the carbocation is formed. Now, Markovnikov's rule is an easy, quick way of identifying the major product. It says that the thing with more hydrogens gets the hydrogen. So if you have H and OH coming from water, between these two carbons, this one has more hydrogen. So this will get another hydrogen. So the major product would be where this is OH and this becomes CH3. Okay, that's the major product. That is this one. That's Markovnikov's rule. The explanation for that is that because this carbon is secondary carbon, it has in positive inductive effect from two carbons, two alkyl groups attached to it, which makes it more stable if the carbocation is formed here. And that is why it gets the more negative thing. The extended version of Markovnikov's rule is that the more stable carbocation gets the more negative thing. Okay, so primary has a lower chance than secondary, and secondary has a lower chance than tertiary carbon. Give the structured formula of U and V. V is basically when you do nucleophilic substitution on OH and Br. So depending on what alcohol you made, if you made the first one, then this will be this one. And if you make the second one, then this will be this one. Just make sure that whatever alcohol you make, HBr also reacts with that one. Don't interchange them. Okay, suggest a suitable reagent and condition for reaction 3. What's on reaction 3? So reaction 3 is again elimination, and you need to remove HBr. You're removing an acid. So what better thing to remove an acid than ethanol? So we need sodium hydroxide, which is an alkali, which must be ethanolic. Why ethanolic? Because we don't want water to come in. Otherwise, water will come and substitute instead of Br, OH will come. And we needed to go to completion, so heat under efflux. Okay. There are 4 alcohols A, B, C, and D, which are structural isomers with a molecular formula C4H10O. Okay, so we have C4H10O, all of them alcohols. Alcohol A does not react with acid to high potassium dichromate 6. So that means alcohol A cannot be oxidized, which means alcohol A is tertiary. So that's simple. Just take this carbon and give it 1 OH and 3 more carbons. So there you go, C4H9OH. That is a tertiary carbon. So that must be A. B, C, and D do, which means B, C, and D are tertiary, secondary or primary. All 4 alcohols react with hot concentrated sulfuric acid to form products with molecular formula C4H8. So all of them do undergo elimination reaction, forming alkene. A, C, and D each give a single product. Okay, so A, because there's only one place where OH can be removed, and all the other places for removal of hydrogen are identical, so you don't get any other product. C and D each give a single product, which also means that C and D must also have a similar situation, where there's either just one spot where you can remove hydrogen from, or 2 identical spots from where you can remove hydrogen from. So yeah, next, B gives a mixture of 2 structural isomers, which means B has an unbalanced situation. On one side, you might have one option for removing H, and from the other side, you might have one other option of removing H. So that might be, I'm guessing, a secondary alcohol. Because then the OH atom has 2 different adjacent carbon atoms, which means it has 2 options of removing hydrogen. Okay, give the skeletal formula for each of the 4 alcohols and complete the diagram with the names and structure. Okay, so isomerism. Let's see. So I can have, let's start with B. B gives a mixture of 2 structural isomers. So B is a secondary alcohol, I know that. And let's just make it a long chain. So yeah, 4 carbons in long chain. Now, obviously, I can have OH here, or I can have OH here. That's one option. I could also move this. Yeah, I could technically do this. I could take this one, this carbon, and move it here, so that I get what this thing. No. Wait a minute. This is not butanol. This is propanol. This is butanol. And this one, now I'll change this. So I'll do OH here, and now I'll give it 2 branches. Yep, now this makes sense. Let's just change this one to this. Okay, so I've already made the one with tertiary carbon. For secondary carbon, I have one option. So OH, and the reason OH on this is B, let me explain why. This is B because when you remove OH and H, you can either remove them from, OH is definitely going away from here, but OH could either go from here and H could go from here, which means it will become but1ene, or OH goes from here and H goes from here, which makes it but2ene. So you're going to get two different products. In this one, this OH is definitely going away from the hair, and there's only one spot where H can go from. So that is this one. So this will become but1ene anyway. And in this one, you have a branch, okay? And because of this branch, no, wait a minute, this won't undergo, this doesn't react for this. So this can't be right. I could have, wait a minute. No, this is right. I don't see what the problem is. Sorry, I got confused. So this is OH coming from here, and there's only one place where hydrogen can go from here, because this is attached to a tertiary carbon that it only has one hydrogen. So yeah, this is also going to give us 2-methyl prop1ene, if I'm not wrong. Yeah, so let's see. So let's just put them there. So this one goes here, that is B, and then C, just take any random one. Okay, just take that one. And this one, OH. Okay, what kind of isomerism is this? This one going to a secondary alcohol is you just change the chain isomerism, or this one is position isomerism, because the chain is still the same, but I have moved where OH is. And this one again is chain isomerism, because I have removed the chain. So why am I saying this is chain and that's not? Because this chain and this chain, they're technically the same. Like this is 4 carbons, this is 4 carbon. The chain is the same, but over here the chain has changed. It's not N anymore. It's like this. It's like a V. So the chain is different. Give the names of the two structural isomers produced by the reaction of B with hot concentrated sulfuric acid. So hot concentrated sulfuric acid. Let me copy B from here. So B was this thing. Let me copy that. Bring it down here. Okay, so when I remove OH from here, one option is to remove it from here, which makes this CH3 CH2 CH with double bond CH2. Okay, that's one option. The other option is I remove OH from here and H from here, which gives me CH3 CH double bond CH CH3. Okay, so those are the two options that I have. State which of these isomers shows stereoisomerism. Stereoisomerism will be the one that shows cis-trans isomerism, right? So that should be carbon attached to two different groups. In this one, carbons attached to two different groups. This one has hydrogen as well as this whole ethyl group next to it. But on this side, it doesn't, which means it can't show cis-trans isomerism. This is attached to both the same atoms, hydrogen. But this one can show cis-trans isomerism because this carbon is attached to H and methyl, and this carbon is attached to H and methyl. So this can show cis-trans isomerism. Okay, so we'll say it is but2ene because each carbon on double bond is attached or bonded to different groups of atoms. But then again, it doesn't explain why this molecule is capable of showing this. So the reason it's capable of showing this is, don't assume that examiner knows about restricted rotation. Talk about it, okay? So there is restricted rotation of double bond, or double bond has restricted rotation, something like that. Draw the displayed formula to show the two stereoisomers. So just take this one. See, always first draw this standard form, okay? The two carbons in the middle like that. And now you have 4 different placements. Doesn't matter how long the chain is. You can all fit them all in there. Focus on the double bond. So I have hydrogen, hydrogen, methyl, methyl, that is cis, and hydrogen, hydrogen, methyl, methyl, that's trans. Okay, so I can easily draw them. But this one will not get marks. Why? Because the examiner said displayed formula. And what did I do? I just made a mixture of structural formula and displayed formula. So don't do that. What I should instead do is open this one up. Make this, give me all the hydrogens separately. That's how I'll score this mark. So pay attention to the way question is phrased. Okay. So this one is going to give me 1, 2, 3 hydrogen, 1, 2, 3 hydrogen. Yeah, there you go. The structure of H is shown. H reacts with both cold dilute aqueous potassium manganate 7 and with hot concentrated. Okay, so with cold you're going to get a diol around the double bond, and the double bond goes away. And with hot you're going to break the double bond. So you're going to get, because these are tertiary carbons, both of them, you're going to get ketones, because notice that this carbon is attached to 1, 2, 3. So when it breaks, this bond breaks down, you're going to get oxygen here. Same for this carbon. Okay, that's for hot concentrated. With cold, you're just going to remove this double bond and get the diol part. But don't forget what happens to this OH. Okay, don't forget that, because that ethanol, or sorry, that alcohol group can also be oxidized to carboxylic acid or aldehyde, depending on what you do with it. Okay, so don't forget that part. Okay, give the structural formula of the organic product of the reaction with cold dilute. So cold dilute doesn't do anything to the alcohol group, but it does react with the double bond. So you're going to break the double bond. Everything else remains the same. You're just going to add two things, one OH here, one OH here. Just put everything else as the way it's supposed to be. So CH3, CH3, CH2OH. Okay, there you go. And it doesn't matter which one you put at the top or on the side or on the left, because these are all single bonds. Single bonds don't have restricted rotation. They can rotate all the time. Give the structure of the organic product of reaction with hot concentrated. So with hot concentrated, what's going to happen is two things. Number one, this double bond is going to break from the middle and you're going to get ketones. So this whole thing will obviously just be prop 2 on. So there's going to be carbonyl group and it has methyl here and the methyl here. So that's that one. The other one, this one, has two parts where it can react. There's the oxygen coming in here because the bond breaks down, and this OH will oxidize. So when it oxidizes, it basically converts to carboxylic acid. So I'm going to get this here. There's a methyl that did not change, but this one changed to COH. Why? Because it is an alcohol that oxidized. Okay, yeah. Complete the reaction scheme to show the mechanism of reaction of H with bromine to form J. This is on p electrons. P electrons they're delocalized slightly. They are rich in with that negative charge will obviously be attracted to any positive charge coming around. And that's what they do. They attack this positive charge. So negative, positive, that's all you have to look at. Just that. Negative attracts positive. That's it. And now as it comes in, negative repels negative. So the electrons that were already on bromine are going to be repelled. They're going to go towards this bromine. Don't think that, oh, this is delta negative, so it's going to repel it. No, because the whole point why you have temporary dipoles in this non-polar molecule is because of this repulsion from coming in pi electrons. Okay, so now what happens? You're going to get carbocation because one bromine is going to be attached to one of them. This pi electrons, both of them, notice that you have pi electrons, right? This double bond. So both of them are going to make a bond with this bromine. So the other one, carbon, is also obviously going to lose that. So it's up to you where you make that carbocation because both of them are eligible. But tertiary carbons, or the carbons with greater alkyl effect, positive inductive effect, have a greater chance of becoming carbocations. But we don't have to go into that, especially when we don't have the values for that. These are both tertiary, so for all we care, they're both good sites for that. So let me just give this one bromine. And now I have a carbocation here. And this is CH3, this is also CH3, this is CH2OH, and this is CH3. And now the bromine, which had a lone pair that was taken from here, will, let me just put the lone pair somewhere closer. So yeah, this is a lone pair. Now this lone pair will attack this. Always remember that the curly arrow shows the movement or the attack from lone pair. Okay, it's the movement of electrons, not anything else. So these electrons go there, attack it, and yeah, there you go. So we have made the compound that we're looking for. Okay. Yeah. Explain the origin of dipole on bromine molecule. I talked about it briefly. It is basically when it comes close to the pi electrons over here, when it comes close to them, they repel its own electrons, and you're going to get temporary dipole forces. So temporary dipoles generated. So it is repulsion from electrons in pi bond or pi electrons causes temporary dipoles, or temporary or induced, that's the word, induced dipoles. Okay, J is formed as an equimolar mixture of isomers. Equimolar means that both of them are equal in amounts and moles, and the reason that could be is because they have equal chance of being made. State the type of isomerism shown by J. What is J? That's J. Let's look at J. J has chiral center. On one side it's methyl, on the other side it's the carbon with two methyls and bromine. On one side it is carboxylic, and on the other side it's bromine. So this is a chiral center. The other one is not, because it's attached to two methyls, and that carboxylic is obviously not because it has hydrogen. Sorry, that's not carboxylic, that's alcohol. But still, it has CH2, so those two hydrogens are not going to make it chiral. But this one is chiral. So let me just put that there. So I put the chiral center in the middle, and I had CH2OH, I had a methyl, I had bromine, and I had that other thing with what was that? CBr and two methyls. Okay, so CBr, I should put C and two methyls. So two methyls and then Br. Okay, or CBr and two methyl. It's your choice how you do it. I can just put this bromine here. Let's just change the position. Let's just move this one here. This way it will be easier to write. This comes here, this comes here. Okay, now I may convert this to a three-dimensional formula. So this is going to be my wedge, and that's going to be my dot. Okay, there you go. All right, now I will draw the mirror here, and now I will repeat this on this side, on this side, on this side, and this. So this is CH2OH. I'm just reflecting it. This is C. Same problem again. So CBr, CH3, 2, and you could move the bromine, because that way it's much easier to write this. Okay, so yep, Br here and 2 here, and this one is Br and that one is methyl. So there you go. I made the two isomers, and this is optical isomers. Okay, yep, that's it.